Good morning, students. The previous session we were discussing on the chapter real numbers. In the last class we are proving root 2 is irrational, root 3 is irrational, and root p is irrational where p is a prime. Okay. Now we are discussing on the some rational numbers. Okay. Revisiting rational numbers and their decimal expressions. Revisiting rational numbers. And their decimal expressions. Revisiting rational numbers and their decimal expansions. You already know about a rational number. The rational number is in the form of p by q, where p and q are integers and q not equal to 0. And also one more thing, a rational number is a terminating decimal expansion or non-terminating recurring decimal expansion. Okay, non-terminating, recurring or repeating. Okay, a rational number is a terminating decimal expansion or non-terminating recurring decimal expansion. Here we have some concepts about the rational numbers. Any rational number is in the form of p by q by observing the denominator. Your denominator is q. Q is not equal to 0. Your p and q are integers. By observing only the denominator or by calculating or by certain simplification, we say that this is a terminating decimal expansion. This is a terminating decimal expansion. Or this is a non-terminating recurring decimal expansion. If we have considered any rational number p by q, just observing or after certain simplification, we observing the denominator, we say that the given rational number is a terminating decimal expansion or non-terminating recurring decimal expansion without actual division. Without actual division, after certain simplification, by observing only the denominator, we say that the given rational number is a terminating or non-terminating decimal expansion. This is one concept here. We have consider some problems, some examples. Okay. Let us consider 0.735. Example 1, 0.735. Example 2, 0.104. Example 3, 0.0875. And example 4, 23.3408. Okay. Just we have observed here. These we know that these are terminating because the decimal expression ends after certain digits. So these are all terminating decimal expression. These are all called the rational numbers. What is the p by q form of this? What is the p by q form of this? So we can write these things as 375 divided by, after the decimal point we have 3 digits, therefore 1 followed by 3 zeros in the denominator. 1 followed by 3 zeros in the denominator. Okay. Now here 104, we can write 104 divided by, after the decimal point we had also 3 digits, therefore this is also 1 followed by 3 zeros in the denominator. Here 875, 0 in the first place. This cannot be considered. Here 875 we can write in the numerator, and in the denominator, after the decimal point we have how many digits here? 4 digits. Therefore the denominator contains 1 followed by 4 zeros. Okay. The next here we have 23 3408 divided by 1. After the decimal point we have 4 digits, therefore this is also 1 followed by 4 zeros. This is the p by q form of these things. Okay, these are all the p by q forms. Just we observe in the denominator, we observe that here 375 divided by 10 to the power of 10 to the power of 3 here. 1000 means what? 10 to the power of 3. 10 into 10 into 10. Okay. 1000. Here is also 104 divided by 10 to the power of 3. Here also 875 divided by 10 to the power of 4 zeros here. 10 to the power of 4. Here 233408 divided by 10 to the power of 4. All the denominators are in the powers of 10. Are in the powers of 10. We observe here. Okay. So all the denominators are in the powers of 10. Then we say that these are the terminating decimal expressions. No. Here also one more simplification is here. So you should consider here 375. This can be written, how we write the 375 as? 375 can be written as here 3 into 5 cube. 3 into 5 cube. 10 cube can be written as 2 into 5 whole cube. 2 into 5 whole cube here. That is equal to 104. 104 means here 13 into 2 square, 2 cube. 13 into 2 cube divided by. Here also 2 into 5 whole cube. Here 875. 875 means here 875 can be written as, okay, this can be written as 2 square into 7 into 521 divided by 10 to the power of 4. Just we can explain. There are some things are more. It take more time to simplify this. You can simplify this one. 875. 875 as a product of primes. Write 5 here. So you can draw 5. 5 ones are 5. 3 remaining 37. 5 sevens are 35. 35 means 2 remain 5 5s are 25. Again 5. 5 3s are 15, 25, 5 5s are 25, 5 7s are 30. Okay. 5 cube into 7. This is equal to 5 cube into 7 divided by 2 into 5 whole to the power of 4. Okay, this is the larger number. For the simplification it takes more time. Okay. So just we consider only these three examples is here. Okay. Now here we observe here this is 3 into 5 cube divided by here can be written as 2 into 5. Can be written as 2 into 5 whole cube. That means 2 cube into 5 cube. 2 cube into 5 cube. Here 5 cube get cancelled. Okay. Just observe. After that the remaining thing is 3 by 2 cube means 8. 3 by 8. This is the p by q form of this 0.375. The decimal number 0.375 can be written as 3 by 8. Okay. Here you observe here 13 into 2 cube divided by 2 cube into 5 cube. Because we have a formula a into b all to the power of m is equal to a to the power of m into b to the power of m. A into b all to the power of m is equal to a to the power of m into b to the power of m. Okay, here 2 cube and 2 cube get cancelled here. 13 divided by 5 cube. 5 cube means 125. 5 cube means 125. Or you can keep as it is 2 cube. Okay, you can keep as it is. This is 5 cube. 5 cube right as it is. Here 5 cube into 7 divided by 2 to the power of 4 into 5 to the power of 4. 5 to the power of 4 can be written as 5 cube into 5. 5 to the power of 3 plus 5 to the power of 1. 3 plus 1, 5 to the power of 4. Again here 5 cube get cancelled. Here 7 divided by 2 to the power of 4 into 5. Just we observe these examples. Just we observe these examples. This is a terminating decimal expansion. In this terminating decimal expansion, the denominator is in the power of 2. The denominator is in the power of 2. And this is also a terminating decimal expansion. Here the denominator is in the power of 5. This is also a terminating decimal expansion. Here the denominator is in the power of 2 and also as well as in the power of 5. We clearly understand the concept. Any terminating decimal expansion is either in the power of 2 or in the power of 5 or in the power of both 2 and 5. This is the concept. By after simplifying, if a rational number, if we have a decimal expansion is given, we can easily say that this is terminating or non-terminating decimal expansion. Okay. By simplifying this, here we can observe that the denominator is in the power of 2 or in the power of 5 or in the power of both 2 and 5. Then we say that the given rational number is a terminating decimal expansion. Okay. When we say that the given rational number is a terminating decimal expansion, the denominator is in the power of 2 or in the power of 5 or in the power of both 2 and 5. Okay. Just we write one statement here. Just we write one statement here. Okay. What is the statement is here? We have a theorem. Not be proved here, but we have a theorem. Theorem cannot be proved here. Therefore, we just do this statement here. Let x be a rational number. Let x be a rational number. Let x be a rational number whose decimal expansion terminates. Whose decimal expansion. Whose decimal expansion. Whose decimal expansion terminates. Whose decimal expansion terminates. Then x can be expressed in the form of x can be expressed in the form p by q, where p and q are co-prime, where P and Q are co-prime, and the prime factorization of Q. Q is of the form from the power of n and 5 to the power of m, where n and m are non-negative integers, where n and m are non-negative integers. N and m are non-negative integers. This is the theorem. This theorem clearly says that x is a rational number whose decimal expansion terminates. X is a rational number whose decimal expansion terminates. Then this can be written in the form of p by q. The p and q are co-primes, and the prime factorization of q is of the form. In the which form? 2 to the power of n and 5 to the power of m. In the powers of 2, or in the powers of 5, or in the powers of both 2 and 5. Then n and m are non-negative integers. This is the theorem we have. Okay. And the next thing is, if the just can reversing the concept here. Just you can reversing the concept. The first example can written here 3 by 8 after simplification of 0 0.375. Okay. 13 by 125. So after certain simplification we say this. Okay. 13 by 125. You can consider only two examples here. Okay. You can write here. You have to observe here the two rational numbers are given. That is 3 by 8 and 13 by 125. Here they given the two rational numbers 3 by 8 and 13 by 125. Okay. This is the terminating decimal expansion. Is a question. 3 by 8 is a terminating decimal expansion. Say yes or no. Okay. How we say that? Or we easily write the decimal form of 3 by 8. How we write the decimal form of 3 by 8 easily? Without actual division. How we write the decimal form of 3 by 8? How we write the decimal form of 13 by 125? First we say that these things are terminating decimal expansion. After yes, then how we write the decimal expansion of these things without actual division? So we know that if a rational number is a terminating decimal expansion, then the denominator must be is in the power of 2 or in the power of 5 or in the power of both 2 and 5. Therefore we can write these things by simplification. 3 divided by 2 cube. 3 divided by 2 cube. Okay. 3 divided by 2 cube. Here 8 can be written as 2 cube. Therefore we say that this is a terminating decimal expansion. How we write the decimal form of this? Decimal form of this can be easily written by how we write the denominator is in the power of 10. When the denominator is in the power of 10, then we easily write. Okay. The denominator is in the power of 10, then we easily write the decimal form of 3 by 8. So for that what we can do? We can multiply here 2 cube. 2 into 5 10. Therefore we can multiply 5 cube by both numerator and denominator. Both numerator and denominator can be multiplied by 5 cube because 2 into 5 becomes 10. The denominator is in the power of 10. Okay. So we can easily write the denominator in the power of 10. Therefore the denominator and both the numerator and denominator can be written in the form of power of 5 or 5 cube. This can be multiplied both numerator and denominator by 5 cube. Why we can multiply by 5 cube? Here the 2 power is 3. Therefore here we can multiply 5 power by 3. Then these are the powers are equal. Then this can be written as 3 into 5 cube. 5 cube means 125 divided by 2 into 5. 2 into 5 whole cube. 2 into 5 whole cube. That is equal to here 3 into 125 into 3. 375. 375 divided by 2 into 5. 10 cube. 10 cube means what? 10 cube means 375 divided by 10 cube. 10 cube means 1000. Therefore 1 followed by 3 zeros. Therefore after the 3 numbers we can put a decimal point 1, 2, 3. Therefore this is 0.375. Therefore the decimal expansion of 3 by 8 is 0.375. In this way we can easily write the decimal expansion of any number without actual division. Now we consider one more example here. 13 by 125. This can be written as 13 divided by 125 means 5 cube. 5 cube. 125 means 5 cube. Now, if you make the denominator in the power of 10, then what we multiply both the numerator and denominator? Which power we should multiply? Okay. Here we have already 5, so it requires 2. Okay. You can multiply both numerator and denominator by 2 cube. Because here 5 is in the power of 3, therefore we can multiply the power of 3 by 2. Okay. 2 cube both numerator and denominator is equal to 13 into 2 cube means 8. 2 cube means 8. Divided by 5 into 2. 5 into 2 whole cube. 13. Here we have already write the no 13 8s are 104 divided by 5 into 2 10 cube. 10 cube. That is equal to 104 divided by 10 cube is 1 power by 3 zeros. 104 by 3 zeros means after the 3 digits we can put a decimal point. That is 0.104. The decimal expansion of 13 by 125 is 0.104 without actual division. Okay. In this way, we can write the decimal expansion of any given number, any given rational number without actual division. Okay. Now we have one more theorem here. That x is equal to more theorem. Let x is equal to p by q. Let x is equal to p by q be a rational number. Be a rational number. Be a rational number. Be a rational number. Such that the prime factorization of q is of the form 2 to the power of n, 5 to the power of m, where n and m are co-primes, where n and m are non-negative integers, then x as a decimal expansion which terminates this is not there here. We observe here x is equal to p by q, where that x is equal to p by denominator is the form of 2 to the power of n, 5 to the power of m, where n and m are non-negative integers. Non-negative integers. Then x has a decimal expansion that terminates. We can write here 3 by 8. Okay, 3 by 8 is equal to 3 divided by 2 cube. That means 2 cube. Here we say that the cube is in the form of 2 to the power of n and 5 to the power of m. But here only 2. What we write about 5? 5 can be written as 5 to the power of 0. 5 to the power of 0 means 1. 5 to the power of 0 means 1. 1 into 2 cube, again you get 2 cube. Therefore, we need not to write 5 to the power of 0 here. So, we can say that here non-negative integers here. n and m are non-negative integers. Okay. So, the denominator is in the form of 2 to the power of n and 5 to the power of m. That means the decimal expansion, what we say that the decimal expansion terminates here. The decimal expansion terminates. And we can take one more example. 13 divided by 125 is equal to 13 divided by 5 cube. Okay, 5 cube. This is also written as 2 to the power of 0. Okay, 2 to the power of 0. 5 cube into 2 to the power of 0 here. 2 to the power of 0 means 1. 5 cube into 1, again 5 cube. Therefore, need not write. The denominator must be either is in the form of 2 power or in the form of 5 power or in the power of both 2 and 5. Then the decimal expansion terminates 0.104. Okay. This way we can easily say that the decimal expansion terminates. Okay. In the last example, we say that the decimal, how we can write the decimal expansion of the given rational number after the simplification. Okay. Here one more theorem here. Here we have one more theorem. Let x is equal to p by q, the rational number, such that the prime factorization of q such that the prime factorization of q is not of the form to the power of n by to the power of m, where n and m are non-negative integers, where n and m are non-negative integers, where n and m are non-negative integers, then x as a decimal expansion, which is non-terminating recurring, recurring. Okay. Here the theorem says that let x is equal to p by q be a rational number. First we say that x is a rational number. Is in the form of p by q. Such that the prime factorization of q is not in the form of 2 to the power of n, 5 to the power of n. In the last two theorems we say that the denominator is in the form of 2 to the power of n and 5 to the power of n. Here, if the denominator is not in the form of 2 to the power of n, 5 to the power of m, but it is a rational number, then where n and m are non-negative integers, then next is the decimal expansion. What type of decimal expansion as x? What type of decimal expansion as x? X as a decimal expansion which is non-terminating and recurring. X as a decimal expansion which is non-terminating and recurring. For example, here write example 1 by 7. Here the denominator is 7. It is not in the form of 2 or in the form of 5 or in the form of 2 to the power of n and 5 to the power of m. Here the denominator is 7. That means we can easily say that it is a non-terminating and recurring decimal expansion or repeating decimal expansion. This is a non-terminating and repeating decimal expansion. Here this is equal to 0.142871. Okay, 142871. It is a repeating group of digits here. 14287 repeats here. Here 14287 is a repeating string. Therefore, 1 by 7 is a non-terminating. 1 by 7 is a rational number. Say that 1 by 7 is a rational number, and it is the decimal expansion of this is non-terminating and recurring decimal expansion. When we say that when the denominator is not in the form of in the power of 2 or in the power of 5 or in the power of what? 2 and 5. Okay. Now in the exercise 8.4 we have some problems here. Exercise 8.4 we have some problems. I discussed today 1 or 2. You can do those things as homework. Okay. Okay. The 8.4 first main, without actually performing the long division. I say that without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or non-terminating repeating decimal expansion. All the given numbers are rational numbers. First they said all the given numbers are here is rational numbers. You should not do an actual long division. Here they say that without actually performing the long division, you do not do the long division process. State whether the given rational number will have a terminating decimal expansion or non-terminating repeating decimal expansion after certain simplification. Yes, okay. Here we consider the one example. 17 by 8. This is a terminating or non-terminating decimal expansion. We say without actual division. What is our theorem says? If the given number is a rational number, if it terminates, then the denominator should be either is in the power of 2 or in the power of 5 or in the power of 4 to 1 5. Therefore 17 by 8 can be 17 divided by 2 cube. Now the denominator is in the power of 2. Therefore this is a terminating decimal expansion. This is terminating decimal expansion. Which one? 17 by 8 is a terminating decimal expansion. Okay. Now we will consider one more example. One more example. 15 by 1600. 1600. 15 by 1600. Here this 1500 is can be written as 15 divided by 1600 can be written as 16 is 2 to the here 16 into 100. 1600 can be written as 16 into 100. Okay. Now this is simply 15 divided by, just we consider 16. 2 2s are 4, 4 2s are 8, 8 is 15, 2 to the power of 4. 100 can be written as 10 square. 10 square. Therefore, this can be written as 15 divided by 2 to the power of 4 into 10 square means 5 to the power of 2 into 2 to the power of 2. Because 10 can be written as 5 into 2. 5 into 2 1 to the power of 2 means 5 to the power of 2 to the power of 2. That is equal to 15 divided by 2 to the power of 4 into 2 to the power of 2 is equal to 2 to the power of 6 into 5 to the power of 2. Therefore, this is a terminating decimal expansion. This is a terminating decimal expansion. Because the denominator is in the power of 2 and 5. Okay. Now we consider one more example. 129 divided by 2 square 5 to the power of 7 7 to the power of 5 7 to the power of 5 2 square 5 to the power of 7 and 7 to the power of 5. Now just simplify 129. 129 is in the power of any power, so you can write 129. 3 4s are 12, 3 3s are 3 into 43. That's it enough. Here 7 to the power of 5. 7 to the power of 5. 129. No cancellations is possible. Here in the denominator 7 to the power of 5 we have. 129 cannot be written in the form of 7 square. Is it possible to write 129 in the power of 7? 7 ones are 7. 7 to the power 7 ones are 7 here. What is remaining here? 559. 59 is not the multiple of 7. Therefore, this is not possible. Here this is non-terminating recurring decimal expansion. Non-terminating recurring decimal expansion. Non-terminating recurring decimal expansion. Here further simplification is not possible here. Further simplification is not possible. Therefore, this is a non-terminating and recurring decimal expansion. What we do here, only we 3 4s are 12, 3 3s are 9. 3 into 43, 129 can be written as 3 into 43. No use here. 7 does not cancel by these things. Here 7 is remaining in the denominator. Therefore, this is here 2 power and also 5 power, but in both with this 7 power also. 7 power is not in the denominator. Therefore, the given number, the given rational number is a non-terminating and recurring decimal expansion. Okay. Now you should consider one more example. 35 by 50. Or any other things. Divided by 50. 35 divided by 50. 35 can be written as 7 5 is a 35. 50 can be written as 25 2s are 25 2s are 50. 5 1s are 5 5s are 7 divided by 5 into 2. Therefore, denominator is the power of both 5 and 2. Therefore, this is a terminating decimal expansion. This is terminating decimal expansion. Terminating decimal expansion, because it is here the denominator is in the power of both 5 and 2. You should consider some more examples. Okay. You should do some other examples as homework. This is the end of this chapter. Okay. We will meet in the next chapter. Okay.